Welcome. Today we're going to be talking about linear motion. Linear motion isn't directly in our curriculum for this year, however it is one of the building blocks of everything that we'll do throughout the year. So it is important that we cover linear motion before we move on to more complicated topics. So the first thing that I want to mention today is the difference between scalar and vector. These are two different types of quantity. A scalar quantity simply does not have direction. So it can be written without direction. A vector quantity must have direction. So an example of a scalar quantity would be anything that doesn't have a direction associated with it, such as temperature, mass, density. Anything like that that doesn't have a direction associated with it. Vector quantities, there's far fewer vector quantities, but they do have directions. So examples would be motion. If you're moving, what direction are you moving in? Or another one would be force. If you're pushing something, what direction are you pushing it in? So today, throughout this year, we're going to spend a lot of time talking about both of these different types of quantities. We're also going to spend a very significant amount of time talking about rates. Rates are simply a quantity divided by time. And so you can take a rate from anything, and you're just simply dividing that quantity by time to see what you get. And so the most significant rate, and the one we're going to focus on today, is velocity. Or you can also refer to it as speed. The only difference being velocity is a vector, while speed is a scalar. And then everything we talk about today will also apply to acceleration. Acceleration, of course, being a vector as well. So, if we go back to velocity and speed, the simplest way to put velocity is it's just the rate of distance divided by time. So I'll abbreviate velocity with a v, and it just simply equals distance traveled divided by the time that it took to travel that distance. So we can do a small example. Let's say that I drove 450 miles in a time of 10 hours. That means my velocity was 45 miles per hour. However, that's only really accurate if I was driving that exact speed the entire time. Most likely I wasn't. I may have stopped to get gas, sped up, slowed down, so on and so forth. And so as a result, this isn't really the exact velocity I was traveling at, but more of an average. So I'm going to write average. Or I can also denote average velocity as v with a line over it. So it gives us an average. What was my average velocity over the course of those 10 miles? And so I can make this velocity more accurate by using smaller time periods. What if instead of 10 hours, I use a time period of 5 hours? That'll give me a much more accurate average velocity over the course of those 5 hours. I could also use 1 hour, and it'll give me an even more accurate velocity. And as long as I continue shrinking the time period, it'll continue to give me a more and more accurate average velocity over the course of that time period. And so it leads to the question of how small can I make my time period? Because the smaller my time period is, the more accurate my answer is. And ultimately, what I want is to get what we call instantaneous velocity. And so the instantaneous velocity is my exact velocity at an exact time. And so the only way to do that is to continue shrinking this time period as much as possible. And so the smallest time period that I can make for this equation is actually a time of 0 seconds. There's no way to get smaller than 0. However, if I divide my distance by 0, you get an error in your calculator. And that's because it's impossible to divide by 0. So in calculus, they came up with what's called a limit. And a limit is a way of circumventing dividing by 0. It allows us to do it in kind of a clever way that allows us to obtain an instantaneous velocity. However, for our purposes today, all we really need to know are 3 kinematic equations that are based off of these limits. And so they are VF equals V naught plus AT, X equals X naught plus V naught T plus 1/2 AT squared, and VF squared equals V naught squared plus 2AX. Now hopefully these 3 formulas look very familiar from last year. You should have used them all the time. You should be very familiar with them. So the last thing that we'll talk about is free fall. The only really difference between free fall and linear motion is that in linear motion you can have any kind of acceleration. In free fall, our acceleration always equals gravity, which always equals 9.8 meters per second squared. And so you just simply make that substitution of A for G. There are a couple of things to note, however. If I throw a ball straight up and then it comes straight back down, because our gravity, our acceleration, is constant the entire time, whatever velocity I throw it up with, let's say it's 20 meters per second, will be the exact same velocity that it hits the ground with, 20 meters per second. And so we can go further to expand this and say that if by this point, if it's slowed down to 15 meters per second, then at that point, on its way back down, it'll also be at 15 meters per second. And let's say up here, it's slowed down to 5 meters per second. On its way down, it will have accelerated to 5 meters per second at that exact spot. And if we continue, we can say at the very, very peak, it'll have a velocity of 0 meters per second. It'll come to a complete stop for a fraction of a second at its highest point before it starts to fall back down and accelerate back towards the ground. Because of this, we can say that our velocity up equals our velocity down. The other thing to note is that if it has a total time of 6 seconds, meaning it takes, from the time that it's thrown, it takes 6 seconds to return back to the ground. That means that it'll take 3 seconds on the way up, and it'll take 3 seconds on the way down. So it'll take 3 seconds to go from the ground to its highest point, and then it'll take an additional 3 seconds to go from its highest point back down to the ground. And so we can also say that the time up will equal the time down. So, I hope all of this has been a review for you. And so now I have a few practice problems for you to try. 2 problems that I want you to work on at home and bring to class tomorrow. If you have trouble with them, we'll talk about them, but please try to complete them and bring them to class. Have a good day.